Okay, hello everyone, and welcome to this new colloquium from the JWST program of the Instituto de Astrofísica de Andalucía. Today it's our pleasure to have with us Professor Ignasi Ribas, who will be talking about the present and future of exoplanet research. So Professor Ribas is the director of the Institute of Space Studies of Catalonia and professor at the Institute of Space Sciences of the CSIC. He has a degree and a PhD in physics from the University of Barcelona and made a postdoctoral stay at Villanova University in the States with a Fulbright scholarship. His work focuses mainly on exoplanet discovery and characterization with the goal of finding new planets similar to our Earth for the eventual search for life. He holds high-level responsibilities in several space missions and astronomical instruments, such as the CARMENES spectrometer, where he is project scientist, and the CAOPS, his board member, PLATO, follow-up coordination, and Ariel copy missions. And he is also deeply involved in the development of nanosatellite projects as part of his role as director of the Institute of Space Studies of Catalonia. He has published about 400 papers in international journals, including Nature and Science. And he has been member of the Astronomical Working Group of the European Space Agency. He has been president of the International Astronomical Union Division G on stars and stellar physics, and advisor of the Spanish Ministry of Economy and Competitiveness. And he's strongly committed to outreach activities and dissemination of scientific results. So, that's yours.
Okay, so thanks very much, Francisco, for the introduction. And let me start by thanking people here at IAA for the invitation. Isabel Marquez, who I don't think she's here today, but thanks for that. And also for the nicely hosting me here and for being so welcoming. Also with Pedro Amado, that we spent a nice morning of discussions, and also with Fran. So today here, I'm going to give a talk about exoplanets, present and future of exoplanet research. And this is obviously a very broad topic. So necessarily my talk will be a bit shallow in terms of I won't go into a lot of depth into some of the topics, but then later during the questions, you feel free to ask anything you think about and we can discuss. So I'm going to give a broad overview of where we are here and where we expect to be going in the next, actually, let's say decades, right? So we'll see that it's a very active field and there's a lot of action here. So there's a lot to be done in the upcoming future. So one thing that has actually happened over the last 3 decades, I'd say, is that we've gone from having a picture of the sky like this to knowing that it's actually like that, right? So nearly every star has a planet around it, or even a planetary system. So we know that today, and I'm going to be discussing this in more detail, there are probably more planets than stars in our galaxy. And this is only knowledge that we have acquired over the last 3 decades, more or less, since the first discovery of an exoplanet around the normal star back in 1995. So this is this year the celebration of the 30th anniversary. So how have we gone from let's say, a star field to a field that we know is full of exoplanets? Now, how do we actually come up with planets? And this is very introductory. I'm sure most of you know this already. But there are a number of techniques that are used to find exoplanets around other stars. So we can go to, we can use how the star varies over time, either by changing velocity, position, or brightness, or some timing methods as well, other more fancy techniques, physics-based, gravitational microlensing, and even in some cases, we can take real pictures of planets. But most of our ability to find planets at this time is through these methods here. These have provided the largest number of detections of the nearly 5,000 exoplanets, actually more than 5,000 exoplanets that we know today. But this is very important to understand that these are indirect methods. So we base our capabilities to find exoplanets on our ability to measure starlight and to make very precise measurements of starlight. Of course, this has many limitations, and I'm going to discuss this very briefly. And in the far future, we'd like to go and take real pictures of stars, of planets, and that would solve some of the issues that we have today. But this is, as you'll see at the end of my talk, for the far future, let's say. So in reality, this is a very simplified picture, and there's a very famous diagram that I'm showing here. This is so-called the Perryman diagram. And you can see here, this is a branching of different exoplanet detection methods. And you can see here that goes dynamical, microlensing, photometry, and each of these branches goes as far down as the ability to find the smaller and smaller planets. So these 10 Jupiters, 1 Jupiter, 10 Earths, 1 Earth. And some of these techniques you can see go down to very, very low masses, let's say. So with radial velocities, with transits, we're able to find really small planets. And this is the complex picture of these techniques, let's say. And one can come up with many different indirect ways to find planets. And this is what we're doing these days. And of course, we also have the direct imaging, which is there, and which I was saying a few minutes ago, they will flourish probably in a couple of decades or so. So let's go and have a look into some of the most successful techniques so far. These are the Doppler technique, the RV method, and the transit search technique. And I'm sure you know already that this was the first successful technique to find exoplanet around a normal star. This is there on the right, 51 Pega CB. This is the radial velocity curve of this star. And Michel Mayor and Didier Queloz reported a half a Jupiter mass planet around this star back in 1995, in October, I think it was. And if one does the numbers and we can understand how one actually gets to these planet detections, one can take, this is our solar system here, and these are the periods of planets in our solar system. And you can see here the predicted or the amplitudes of the radial velocity motion caused by those planets on our sun. So it's actually, Jupiter is easy, let's say, easy-ish. It induces 12 meters per second amplitude on the sun, but look at the other planets, right? So it's really tricky. And if you go to the Earth, we're talking about 9 centimeters per second effect. And if you go to the smaller planets, it's even at the millimeter per second effect. So this is really the challenge here, is to be able to determine velocities of stars to the precision of a meter per second or less, actually even centimeters per second. So over the last 30 years, there's been lots of developments in terms of instrumentation. I'm not going to cover those. There's many instruments out there, you know, probably about HARPS, you know, about ESPRESSO, you know, about many others, NUIT, HPF. So there's like maybe a dozen instruments these days doing precise radial velocities. But there's one specific instrument in which we've been investing a lot of effort here, which was led from the IAA in collaboration with Heidelberg. And this is the CARMENES instrument. So CARMENES instrument has been using this technique of doing precise radial velocities over a long period of time to try and measure, or actually try and discover exoplanets and measure their masses, or at least their minimum masses. So this is mounted on the 3.5 meter telescope in Palo Alto, so next door, and it was developed by a consortium of 11 Spanish and German institutions. I'm sure you already know about CARMENES, but I'm going to show you some of the newer results. At the beginning, we started back in 2016 collecting data, and we ran a GTO program of 750 nights. And since 2021, we are running this CARMENES Legacy Survey and CARMENES Legacy Plus. That's going to go up to 2026 and perhaps beyond that as well. And there's about 600 nights that are being invested in this. So CARMENES is a two-channel precise radial velocity instrument spectrograph. It has a visible channel and a near-infrared channel, which, by the way, the near-infrared part was developed here in-house at the IAA through a lot of effort. I'm sure you know maybe the stories already, but now it's performing incredibly well. And the goal of CARMENES was and is to detect and characterize low-mass planets around M dwarfs. We're talking about the smallest stars in the galaxy, from, let's say, 0.5, 0.6 solar masses down to the hydrogen burning limit at 0.08 solar masses, more or less. And we want to understand the architecture and the statistics of those planetary systems. So CARMENES has been extremely successful. We have already discovered anew over, it's around 40 planets. This is a plot that shows planet mass in Earth masses versus the stellar mass. You can see that we have, these are RV planets, or planets discovered with the Doppler technique. There's a lot of discoveries in the neighborhood of 1 solar mass. These are the sun-like stars. There's a lot less here when we go to lower and lower masses. And this is the natural CARMENES hunting ground here, from 0.1 to 0.6 solar masses. And you can see here, black are the symbols from literature, and the symbols in color are the discoveries from CARMENES. You can see here that we've contributed a very significant number of known exoplanets around low mass stars. And actually down here, let's say below 0.25 solar masses, which is the fully convective limit, I'd say more than half of the known exoplanets with masses determined from radial velocities have been provided by CARMENES. Some of the two colors show that in some cases we find planets from our blind survey. So we take a star and we hit it for 100 times, trying to find some periodicities. And some other cases we go and we do follow-up of known or at least candidate transiting planets, and then we measure their properties. And this is the difference between the blue here, which would be a test follow-up, and the red here. And CARMENES has uncovered a full zoo of planets, planets in Neptune's in temperate orbits, close-in eccentric planets, that have very active star hosts, nearby systems that have transits as well. So you name it. There's lots of different kinds of planets that CARMENES has found. Let me show you, I'd say my favorite CARMENES discovery in terms of exoplanets is this nice system around T Garden star. T Garden star is one of the closest stars to our solar system. It's only 3.8 parsecs away, and it's a really, really low mass star. It's M7, so it's about 0.1 solar masses. And we found a very nice system of 3 planets. The amazing thing, you can see the properties there. The amazing thing is that they have masses or minimum masses that are almost identical to one Earth mass. So these are really Earth twins, let's say. Of course, orbiting a star is very different from our sun. And actually, 2 of those planets, planet B and planet C here, are within the habitable zone of this star. So it's really a system of habitable planets or potentially habitable planets actually next door. And this is one of the major discoveries that CARMENES has produced among many others, let's say. Some other results are coming up, and this is fresh from the oven here. We have one surprise that has been, CARMENES has also been finding giant planets around very, very low mass stars to a surprising abundance, let's say. So we do some plain occurrence rate calculation. We find that about 6 to 7% of the late or the M dwarfs host giant planets. And this is sort of a surprise because we were not expecting that high rate. And actually not even models expected such high rates. You can see here, this is amazing, actually. It's 9 years worth of CARMENES data, and there's 2 clear planetary signals. You can see one going up and down and the other a smoother, let's say, or lower period there. And this is the phase folded diagrams. And on the right, you have there the predictions from models in black, or these little dots, and the stars show the location of these giant planets around these stars. So they're really sitting in an area of this parameter space that is not occupied by simulations, which means that these models cannot reproduce the properties of those planets. Now, it's probably because the mechanism that forms these planets around these M dwarfs on white orbits and being giants are not described by these models, which are based on the core or pebble accretion scenario. And probably there's another scenario or another mechanism that can explain these really large planets around these really small stars. So there's a paper that will be out probably this year. This is by Juan Carlos Morales, that's in preparation, that will be discussing these results from CARMENES. And the other big thing from the CARMENES survey is the determination of occurrence rates. And here we're talking about, the question is, how many planets are orbiting M dwarfs? And is this number different from sun-like stars? So we find in our statistics that 1.5, each M dwarf on average hosts 1.5 planets, which means that there's more planets than stars. Right? And actually 94% of stars have planets as have been found by CARMENES. And about 1/3 of the stars have planets within the habitable zone. So this is the famous Eta Earth number. So this is the abundance of planets in the habitable zone of a star. For these M dwarfs is 1/3, which is quite amazing, actually. And as I said already, that there's an excess of giant planets that we're not expecting, and even beyond that. Now there's a paper that has just been submitted by Andrzej and Kamiński that in the case if we home in on the really, really smallest end of the masses for these targets, so below 0.16 solar masses, we find even higher abundance of exoplanets, at least above 2 planets per star, and very strongly dependent on planetary mass. So this is the number of planets that we have in different period bins as a function of planet mass. And the really small planets that can be potentially rocky, between 0.5 and 3 Earth masses, are extremely abundant. There's actually almost 2 per star. Where when we go to what we call sub-Neptune mass planets, they're not quite as abundant, but they're also there. So it's amazing to think that all these little stars have planets and probably have multiple planetary systems with more than one planet in orbit, let's say. And this is some of the major results that have come out from CARMENES, which I already mentioned. I cannot stress enough. It's being operated here next door by our friends at Colorado. Now, one of the things that CARMENES has been doing is helping us to meet our neighbors. So we're talking about the nearest exoplanet systems. What are the nearest stars, and whether the question is whether they have planets. And the result is that yes, these are on the right here. You have the 40th nearest planetary, stellar systems to our solar system, and about half of them have already planets have planets that have been found around them, and a fraction of them, haven't done the numbers, but it's probably 1/3 or so, have been uncovered by CARMENES, which is focusing us again on these M dwarfs, and therefore these are our immediate neighbors. So we are actually getting to know what is let's say a planetary census of our immediate neighborhood. So if you ever feel like taking a trip and going to some nearby star, and it's going to be most likely one of these planets, and it could be one of the CARMENES planets actually. So I'd go to the Garden Star, by the way. It's 3.8 parsecs. It's okay. But it's not the only research being done here, and I'd like to mention this specific result. Proxima Centauri, so the nearest stellar system to our solar system, also has planets. And this was discovered by a team led by Guillem Anglada-Escudé back in 2016. By the way, the second author of this paper is sitting here in the audience. That was Pedro. So there was also strong participation here. And you can see that with HARPS, it was possible to uncover Proxima b, which has a mass of about 1.3 Earth masses. But now, even with more precise data using ESPRESSO, and you can see here the evolution from the HARPS data to the ESPRESSO data here on the right. This is Proxima b, so it's unmistakable, so it's there for sure. There's also another planet called Proxima d, which has a mass of 0.3 Earth masses. So this is the state of the art. We're able already to find planets as small as, or as low mass as 0.3 Earth masses. So this is about 1/3 of the Earth, or about 3 times Mars, actually. That's what we're doing today when we use ESPRESSO data. So this is where we are in terms of radial velocities. Now, the other big thing is transits, right? Transits is the other technique that has been extremely successful, actually even more than radial velocities. There's about 1,000 planets found with RBs, and there's about 4,000 or so found with transits. Now, this is very simple. We're talking about measuring brightness of stars and trying to find little dips in this brightness, which are happening when a planet crosses in front of the stellar disk. And then from the depth of that measurement, one can actually, from the depth which is measured, one can measure the radius of the planet, as long as you have a good measure of the radius of the star. Now, things are quite easy when we talk about Sun-Jupiter systems, talking about 1-2% transit depths. But when you go to the Earth, things become a lot more complicated. And we're talking about 80 parts per million when we go to an eclipse of an Earth in front of the Sun, and an M dwarf in front of the Earth is about 0.5 or so %. But when one has both transits and radial velocities, so masses and radii, one can measure densities and therefore go to plots like this one, planet radius versus planet mass, have some theoretical expectations on depending on the composition of those planets, like being rock, iron, water, volatiles or so, or anything, or any other combination. One can actually more or less guess, let's say, or have an indication of what is the bulk properties of those exoplanets, which also convey a lot of information. So now in terms of transits, the big revolution was when transits, there were space missions. The first one was Corot, which also had strong participation from people here in Granada, the IAA. This was followed by Kepler plus K2, Cheops also flying there, and TESS as well. So these are the missions that we have that are contributing these planetary transit measures and they have uncovered thousands of transiting systems, let's say. So and TESS, by the way, is continuing operations and survey, and so is CHAOPS, which is not running a survey, but characterizing planets with transits. So let me just quickly go home in on some of these missions. CHAOPS was launched back in 2019, and it's a S-class mission, a small mission from ESA. Now it's called F. So there's a call that will be out very soon for these kinds of missions. And you can check the publications there on how TESS is performing. CHAOPS is performing. It's really nice. And there's lots of highlights and lots of results. Probably the most, I'd say the one that has attracted more press attention, that was Rafa Luque's publication from a couple of years ago, where we, from CHAOPS and a number of other facilities, we could uncover a system of 6 exoplanets around a star in a Laplace resonance. So there was a chain of resonant orbits around this star, and this was only possible because it was a detective game, right? So there were a few of these transits which didn't make any sense, and then it was the whole picture became clear when trying to assume, let's say, a commensurability of these orbits because of resonance, and trying to program CHAOPS observations and trying to hunt for these new planets, and indeed a 6-planet system was uncovered. This was really impressive. This is a Nature paper from 2023. By the way, the GEO program of CHAOPS is open to everyone. It will probably open soon, and so if you have any idea for a precise photometer from space, feel free to put in proposals. So it's really worth doing if you have this interest. Now, what's there in store for us for the upcoming future in terms of transits? The big mission that is coming up is PLATO, right? And I'm sure you also know PLATO, which also has strong participation from people here at the IEA in Granada. Talking about a combination. So let's say the focus here is to look for Earth-sized planets. We're not talking about TESS, is more focused on Neptune, sub-Neptune, and so on. PLATO is going for the true Earth-Sun analog system. So we're talking about Earth radius planets around Sun-like stars. So it means finding transits of objects that induce a depth of about 80 parts per million and have a period of 350 or 360 days, which is a big challenge. And then following those up. And so this is a mission that is, technically, this is ESA's M3 mission, and it's a platform of many telescopes, 24 plus 2 telescopes. And this has a launch plan for end of 2026. So only in a couple of years' time, actually. In a couple of years' time. Now, the method that PLATO will be using is a combination of finding these very small planetary transits and the ability to characterize the stars. So it's going to use astroseismology to get also precise photometry and understand stellar or measure stellar properties from that astroseismology. Talking about radius, mass, and age, which is usually a parameter that's very elusive, and PLATO should be giving that. So by combining the measurements, the photometric measurements from space with a ground-based program of radial velocities and other facilities, also imaging, one can get a full characterization of the planet and the planetary system. So, and the star. So radii of planets down to 3%, masses down to 10%, and ages down to 10%, which is also a sort of a holy grail here, because we want to be able to do planetology and to understand how planetary systems evolve over time. So age is usually not available, but for this sample of PLATO, which will have astroseismology, that should be also possible. Now, PLATO will, for now, will focus on a southern field. This is there on the top right, there's the map of the sky. And it's going to focus on this southern field for the initial 2 and maybe 4 years. And it's going to cover an area of about 2,000 square degrees. Remember that Kepler was about 100 square degrees. So it's way larger than the Kepler field. And this will be done for years, for several years, which means that it will have also long period objects. So I'm not going to go into details. You can see the numbers there. It's going to be monitoring thousands of stars for these exoplanets, for these little dips. In particular, also M dwarfs, some specific sample there. And the goal is to detect thousands of exoplanets, maybe 4, maybe 5, maybe 6,000 or so. And a subsample of those, of order of 100, this should be true Sun-Earth twins, let's say true Earth analogues. For now, we have 0 of those. Not even Kepler was able to find any of these. And from Plato, we expect to find about 100 of them. Now, moving on to what is known from these years, let me just give a few headlines. Talking about, I said already, we know today that we have more planets than stars in our galaxy. I think that's a big result. We know as well that there's many planetary systems in the galaxy, so more than one planet around each star, and especially when we go to low mass stars. The most common type of planet in the galaxy are super Earths, sub-Neptunes, and maybe also Earths, which is which still not uncovering. But sub-Neptunes are really abundant. Super Earths are really abundant as well. So there's many systems with those super Earths and sub-Neptunes, which, by the way, it's a type of planet that does not exist in our solar system. We don't have any sub-Neptunes or super Earths. And this is for now the most abundant type of planet in the galaxy. And as I said, planets are so abundant that we have even one next door. Right? Our nearest neighbor has a planet which actually is even in the habitable zone, which I'm going to be explaining in a second. But in spite of these very many advances, there's many open questions still, right? So, for example, among the big open questions, this is by no means an exhaustive list, but there are some outstanding questions that are really difficult to address. One of the things, for example, is that we find planets that are too large for models to explain, that they're puffed up beyond anything that theory can explain. For example, we find planets that have radii in excess of 2 Jupiter radii, and this is very difficult to explain. So there are some fancy ways to try and explain these puffed up planets, but it's still a challenge. And this is known from 1999. So it's been a while, and this still, I would say, still an open question. Another open question that we have these days is to understand what is the transition between rocky worlds and gas-rich worlds. So what is this cosmic shoreline that sometimes is alluded to? So where is the distinguishing parameters and mechanisms that can separate planets that resemble our Earth, so with a rocky world with a thin atmosphere, from planets that resemble, let's say, Neptune, which is a gas planet. So this dividing line, let's say, is still under discussion. There's a lot of action, there's a lot of interest there to try and resolve that. And by the way, one of the important works here was by Rafael Luque and Enrique Payet in Science, and the Science magazine 2022, trying to put out a mechanism there alluding to a formation, let's say. So I've been discussing detection of exoplanets, but let's go one step beyond and let's try and understand what exoplanets are made of. And this is, we could call exoplanetology. And it's about, for now, measuring the properties of atmospheres of exoplanets or exoplanet spectroscopy. And the measurement principle for now is to use transits and occultations of transiting systems to try and measure this, let's say, the opacity or the transparency of an atmosphere as a function of wavelength. And you can see here in this diagram is quite obvious. By measuring the depth of the transit, one can actually get information about these atmospheres, and with eclipses as well. When the planet goes behind the star, there's also information. Typically in the thermal infrared, that's where the planet emits light. So if we home in on transmission spectroscopy, we're talking about planets going in front of their star, and therefore we have a disk of a planet that cools a star, and of course it has a ring of atmosphere there, and depending on the opacity of this ring of atmosphere, depending on whether it's transparent or opaque, one can get a transmission spectrum when we observe as a function of wavelength. So at different wavelengths, the opacity will change because of the molecules or atoms that are in that atmosphere, and by measuring this different opacity, which one can get this transmission spectrum. And in the end, the observable are changes in the depth of the transit, right? So this depth of the transit will vary depending on how large the cross-section of the planet is, and that will depend on the opacity of this atmosphere. So it's quite easy to work out. It depends on how dense the atmosphere is, because if you have a dense atmosphere, it's going to be smaller. If you have a puffy atmosphere, it's going to be larger, and therefore have a larger signal. And for the case of hot Jupiters, we're talking about signals of order of 100 parts per million. When we go to Earth, sun analogues. We're talking about less than 1 part per million, which is just undoable. And Earth's around M dwarfs, we're talking about tens of parts per million, let's say. This is the size of this signature of an atmosphere on an exoplanet transit. Now, this was the state of the art a few years ago. This is HST, and on the right there, you can see a number of transmission spectra of a collection of Jupiters. The measurements are these little circles with error bars, and the solid line, this is the model fit, let's say. And you can see that there's not so many measurements there, and sometimes the fits are so-so, let's say. And this is what we had previous to HST. Now the revolution has come with JWST, right? So these are real observed transits with JWST from a paper a couple of years ago at different wavelengths, and by measuring super precise depths for these transits, one can get the transmission spectrum that you have here on the right. And there's no model on these lines to guide your eye. So this is really, these wiggles are really caused by different chemical compounds, typically molecules, on the atmospheres of these exoplanets. And we have a collection of them already. And there's signals that you can see very, very easily with your eyes. For example, CO2 there at 4.3 microns, 4.4 is super easy to see. Actually, let's play a game now. And this is so easy these days, easy-ish, that you can actually see an atmosphere of an exoplanet with your own eyes here, right here. And you'll see here, this is a transit of an exoplanet, this was 39b. This is JWST data, and you have there the wavelength. This is 3 microns. So let me play this and see if you can see the atmosphere of this planet. Did you see it?
Yeah.
It is very obvious, right? So the signal is so strong. So at 4.34, you see clearly the depth of this transit going larger, right? And the extra depth is because CO2 on the atmosphere of the exoplanet is absorbing part of the light, and then the transit is a little bit deeper, right? By about a few hundred ppm. So that's the quality of the. I mean, a few years ago, this would be a dream in a way, right? So this is the data that JWST is now producing sort of routinely. Now, what is the next step in this? And the next step is a fully dedicated mission to exoplanet transits. And this is called the Ariel mission. Ariel is ESA's M4 mission, talking about the launch in late 2029. And it's not going to observe dozens of exoplanets, it's going to observe thousands of exoplanets, maybe 1,000 or more. And the idea is to have a sample analysis of exoplanet atmospheres to understand what they're made of, if there's any trends, what is the connection with their host stars, and what is the connection to evolution, formation, and many of these other parameters. So this is Ariel, and we're heavily working on Ariel these days. So the way Ariel is going to do this is going to start with a large sample of about 1,000 exoplanets. And this will be sort of a general survey there of the atmospheres, fairly shallow, let's say. There's going to be a subsample of these, a few hundred or several hundred exoplanets that is going to go deeper into these objects to understand some of the atmospheric properties in more detail. And there's going to be a smaller collection of this exoplanet transit that is going to be really, really observed to a large depth, and also as a function of time. So we could have also indications about meteorology, let's say, on these exoplanets, if there's any sort of variability. So there's a number of questions that you can, or topics that you can see here on the slide, on the what Ariel is going to try to answer: circulation, variability, color diagrams, phase curves, all sorts of things about these 1,000 exoplanets, some of them observed in great detail. So what is Ariel? Ariel is an infrared telescope, a space telescope. It's about 1 square meter in collecting area, and it has an instrument that has full coverage from 0.5 to about 8 microns in a shot. It's actually several different instruments. There is strong participation here from Spain as well in some of the mechanisms, some of the telescope assembly, and also some in the ground segment. And it's being developed by a consortium of 17 countries in Europe, plus NASA is also a partner there. So that's the mission that's to come, let's say. And it will take JWST observations, which are extremely valuable but more focused on a number of, or a smaller sample to the next level by observing everything that is within its grasp, let's say. So, and get a more of an ensemble analysis of the planet population. Oops, sorry. So in this landscape, maybe one can think, what is our, let's say, what are the main hurdles? What are the main obstacles to make progress? And there are some obstacles, and one particular one that I'm especially interested in that is worth pointing out here. And as I said at the beginning of my talk, what we measure is starlight. We refer our measurements of the planet, even the discovery of it, to our ability to measure the starlight. So what if the star does not cooperate? And that's the main problem, right? Stellar activity is the main problem to make big advancements here. And the reason is that, of course, stars are magnetically active, and they vary at different scales, and they vary with different amplitudes, and that causes a lot of problems, not only for radial velocity determination, but also for transits and for atmospheres as well. Everything is affected if the star is not a homogeneous, quiet gas sphere, which is never the case, right? So I was at a conference a few weeks ago, and it was really embarrassing, right? Because what we want to do is to throw out the star, let's say, but the star does nothing. Everything that people, I mean, I see Jose Carlos there studying the sun in an exquisite level of detail, and this is just a nuisance to planet hunting. So if the star did nothing, planet hunters would be extremely happy, but it's not the case, right? Stars do stuff. And you can see here, this is a plot of our ability to find planets as a function of the amplitude of the radial velocity, as a function of discovery year. And you can see very clearly at the very beginning, we were making lots of progress into going to smaller and smaller planets, but we have stalled. We have stopped at around 1 meter per second or so. And you can say, well, you guys cannot build instruments that are good enough. No, not true. We have instruments that can do much better than this 1 meter per second these days. But we are not pushing below that level, because the main obstacle now is not the precision of the instruments, it's our ability to, let's say, correct the contaminating effects from stars. And the same can be said about transmission spectroscopy. It's the big problem, let's say. So the fundamental limit is no longer instrumental, but it's actually astrophysical because of the knowledge of stars. And it's mostly because of rotation and evolution of active regions. So now this is the part I'm actively working on now these days. And I have this ERC advanced grant called Spotless, and the idea is to use a lot of data from different facilities to use physics and the information that we have on stellar variability by running a simulator, and then try to reach to the level of 10 centimeters per second and 10 ppm, which is absolutely key to get to Earth-Sun analog systems using a variety of different tools. I'm not going to go in detail. If you want more information, we can have a chat later on. So it gets a lot more technical here. So I think that we can confidently say now these days that we know the answers to these questions, right? Are there other planets out there? Yes, and not like in large numbers. So we see planets everywhere. How did they form and evolve? Well, maybe we still don't know, but with JWST and Ariel, we'll have pretty good indications of that. Same with what they are made of, right? So we're trying to get a lot of information on their chemical compositions. But there's still some outstanding questions out there. Are they habitable? And are they inhabited? So can we find actually life or a biosphere on those planets? So this, I think, is a societal revolution, right? So the time when we are able to find life somewhere else in the universe, that's going to be a transformative result. So if Copernican revolution set our place in the universe, let's say in the physical universe, this finding of life on other planets should set us in the context of the living universe. And this is one of the big questions, I think, that we have to answer. Are we alone, let's say, or are we do we live in the only inhabited planet in the universe? And we have a chance to see that happening in the next coming decades. So let's first very quickly talk about habitability. I think everyone knows this, but we're talking about planets that reside in the habitable zone, which is the orbital interval around the star where one can have liquid water on the surface of a rocky planet. And this is this blue swath here on this plot, which of course depends on stellar mass strongly, or stellar luminosity, by the way. So it's from the sun to really small stars. And of course, there's one other ingredient. It's not only the radiation that one planet gets from the star, but there's also the let's say, the protective or the temperature difference that greenhouse gases make, right? So one has to have information about the composition of the atmosphere, and by using the CO2 the amount of CO2 in the atmosphere, one can expand this habitable zone, because you can have zero CO2 here, a lot of CO2 there, and still keep within the habitable range, let's say. So one of the important areas of development is trying finding planets that reside in this so-called habitable zone. And we indeed have already a sample of them. We actually have about, being conservative, maybe 30 or so that we know today that are rocky planets in the habitable zone of nearby stars. And remember, 30 out of 6,000 exoplanets known. So it's really low numbers, not because they're not abundant, but because they're hard to find. So we're still trying to find them. And when we have planets in the habitable zone, we call them potentially habitable. So they could have liquid water on the surface, but we don't know if they do have liquid water, which we would call habitable. And of course, we don't know whether there's any biosphere on that planet. So the answers to this sequence of questions should come from trying to look for biosignatures in the atmospheres of these, or in these exoplanets. So biosignatures are objects, substances, or patterns that require a biological agent to explain, let's say. And of course, we have to do this by remote sensing, right? So you cannot go to the exoplanet and look at, what was it, spiders that are, let's say, this size that are looming around. No, we have to do this from a distance, and we have to be able to find how this life may have altered the properties of its planet, and most importantly, probably the atmosphere. And this is what we call a biosignature. And there's different kinds of biosignatures, so gaseous, surface biosignatures, temporal variability, and the most, let's say, sought after indication would be a indication of oxygenic photosynthesis, which would mean oxygen and CO2, potentially also methane. So these combinations of gases are the ones that we're looking at, trying to look for in other planet atmospheres. So when one has a combination of these biosignature gases, one can be more or less sure, with a bit of uncertainty still, that this can be caused by a biological agent and not by some abiotic process. And the thing will be that, right? So understanding whether a combination of gases in one of these atmospheres is related to a biological process and not to a abiotic process. But in the first stages, the idea is to try and find key molecules related to life, like oxygen or ozone, which is about the same, CO2, methane, gaseous water, and so on. So one obvious question is, can JWST do this? And the answer is no, probably not. Probably not, because even if you do the calculations for the most favorable cases, like an Earth orbiting a very low type star around the corner, it's really difficult to do, because we're talking about signals of order of 2 to a few 10 ppm or so, with water vapor having a signature of at only a few ppm. So this is, remember, transit depth as a function of wavelength, and you can see different molecules that are related to life, and you can see this is 10 parts per million, and you can see water here and there and there, methane is there, okay, CO2 is easy-ish, O3 is also possible, but really this would be an ideal case, which we don't have for now. So how can we hope to have biosignatures in the upcoming future? Well, from the ground, there's some facilities that may actually give us a chance. And there's one instrument called Ristretto, which is now being built for the VLT, for a combination of sphere and I think it's espresso. And this should be able to find or characterize, maybe find oxygen on Proxima B if there was an atmosphere there. So, but this is really an instrument built for the sole purpose of looking at the atmosphere of Proxima B. That's quite something. So we'll see if this happens. It should be have first light in a couple of years' time. And then the big hope, that's the Andes instrument, which there's also participation here from the IAA, which it's a 39 meter diameter telescope at the EELT, and this high resolution spectra covering the visible and the infrared part, which should be able to observe some of these transiting exoplanets around M dwarfs being rocky, let's say of planetary of Earth mass and try and see if there's atmospheres can be characterized. So this remains to be seen, and this will be transit observations, which, by the way, will be affected by stellar activity as well, and we have to really understand how this goes. But the big hope for the future, and that's why I said that there might be ways forward. These are the big space missions that are now being developed. One is the Habitable Worlds Observatory from NASA, which was approved on the NASA Decadal Survey about 3 years ago, and this is moving forward. Although there's some hiccups and there's some stops, but now it's moving forward. And this is a 6-meter diameter telescope that is going to do coronagraphy. So it's going to occult the star with a coronagraph, do let's say, an artificial eclipse of the star to try and reveal the exoplanets that are orbiting the star. You can see it's not very visible here, but there would be a black circle here and the planets orbiting back and forth. And this is the kind of observations that we want to get so that we can take observations of the planet themselves, not related to the planet, to the stellar light, let's say. So this would be the hope for the future. The only problem here is that we're talking about mid-2040s. So, okay, I have to be a bit patient, let's say. And LIFE, this is a European mission that is successor to Darwin. Some of you in the audience may remember Darwin. It's about the same concept. So talking about nulling interferometry in the infrared, roughly at 10 microns. Talking about 5 spacecraft, 4 telescopes of about 2 meters in diameter, and then 1 beam combiner. And this technique is here nulling interferometry, and it's different from coronagraphy in the way that the idea here is to make a destructive interference of light at the center of the beam so that you can destroy, let's say, starlight, and have a constructive interference at some distance from the star, which would be revealing the planet light, right? So it's a fine-tuning of all these different distances of this spacecraft to try and get a minimum at the center and a maximum where you expect to have the planet. So this is the concept that is being developed, and it's actively being developed. And actually, ESA issued some years ago this ESA Voyage 2050, and this was the highest ranked theme, not mission, but theme in this survey for exploration, for, let's say, astrophysical missions. So, and I'm already wrapping up. I've talked about a number of different missions and experiments here, and this is a slide that has pretty much everything that I know of. And you can see how active the field of exoplanets is. So in the past, we've had space missions like Kepler, Spitzer. Now we have TESS, HST, CHEOPS. Gaia is also going to find lots of exoplanets, like JWST. And also there's a lot of activity on the ground with Doppler spectrographs, transit searches, radio, microlensing, imaging. And for the immediate and a bit longer term future, there's a lot of activity as well. PLATO will be launched in 2 years' time, Ariel in 4 years. HWO, who knows when, but should happen as well. LIFE, hope it does. And then the large size telescopes like the EELT, GMT, maybe who knows if TMT will ever happen. But there's going to be activity in this field into well into the 2040s because of these space missions. Again, with many challenges from not only from technology, but also from understanding both planetary properties and stellar properties, and this is what many of us are doing these days, besides also trying to uncover new planets. So I'm going to finish with an iconic picture, and I'm sure you know here in the audience. I mean, when I show this in public outreach talks, no one knows what this is. I hope you guys do. And this is what exactly we're trying to find, right? So the missions that will have to be flying in the 2040s, it's about finding those pale blue dots and characterizing them. So the idea is to actually get pictures of those pale blue dots and also get spectroscopy of those pale blue dots to see the signatures in the atmospheres of these planets that would be indicative of an atmosphere, and even beyond that, of an atmosphere that has some biological imprints, let's say, in forms of these gases, CO2, methane, oxygen, and the likes. So this is what will keep us busy until retirement, I guess, or in beyond. Let's see. All right. And I stop here. Thank you very much.
Thank you, Ignasi. The talk is open for questions. Pedro, you will chair the session, please.
Yeah, it's a pleasure. It's a pleasure. First, I will thank again Ignasi for a very nice presentation. It's impressive how much work we still have ahead of us. So
Yeah.
we have done a little, but we are contributing to it. Indeed. So if anyone has a question for Ignasi, okay, Ronnie.
Hi, thank you very much for the very interesting talk. I do stars. So when you said you wanted to throw them away,
By the way, I do.
didn't hurt my feelings at all.
No, okay, I do stars as well, so I like them too.
It's not my point of view.
Yeah.
You said at some point that the galaxy contains more than anything sub-Neptunes. Is this from what we see, or is this also what we expect? I'm thinking of the parallel with stars where we have an initial mass function.
Yeah.
And for one intermediate mass star, we find 200 tiny pebbles. Do you really expect some Neptunes, or do you expect to be swamped with Mercuries everywhere?
No, there's supposed to be a mass distribution, which probably picks at the some Neptune super Earth distribution. Of course, these models, these theoretical models, are tuned to the data, right? To some extent, all modelers try to fit data, and so far we haven't been able to characterize the population of planets that are below 1 Earth radius, let's say, way below 1 Earth radius. But it's not surprising. I mean, all models seem to reproduce that there's a large population of sub-Neptunes and super Earths. That's not a surprise. There's probably also a large population of Earth-like planets, which is there as well. To me, the most surprising thing is that the most common planets in the galaxy are not there in our solar system. But we haven't seen any solar systems yet. So in this 6,000 exoplanets, there's no single solar system because we cannot find planets as small as the ones we have here. So there's a whole discovery space still to be unwritten.
You cite Rafael's work where he finds 6 sub-Neptunes.
Yeah.
There's a balance there.
And there's many other systems where they are actually lots of these sub-Neptunes are very, very common. But there's an area of the discovery space which we haven't even touched, and PLATO should be doing that, right? Should be going like smaller planets in wider orbits, and we'll see what's there. My impression and what models seem to predict is that there's going to be an abundant number of exoplanets there as well. Yeah.
Thanks for the talks again. So I have a question about the contributors. You said that these inflated contributors they are not explained by models. And what models are you referring to? Is it the formation models or the cooling models?
It's the structure models more than formation. Yes, the problem is that when you run a formation model and also structure, the planet will tend to compress more than we observe, let's say. And then the way to try and explain a puffed up atmosphere is by injecting energy somewhere. You can think maybe those planets are heavily irradiated because they are typically hot Jupiters. So you could think, okay, I'm going to swamp them with energy so they puff up. But the problem, this does not work because the energy is deposited very high up in the atmosphere of this planet and doesn't puff up the planet. It just runs escape processes. So it actually evaporates the planet instead of puffing it up. So you need to put energy at deep layers there to make the planets puff up. Then there's some theories there. Maybe they say that even if it's very circular orbit, but even if it has a tiny amount of eccentricity, there's going to be enough tidal energy deposited to puff up. But there's really no strong evidence of any eccentricity in some of these planets. Now, the current model that explains this better is something called ohmic currents, which seems to be depositing energy where it's needed in a way to puff up. But I don't think the whole issue is settled. There is some explanation. There's still not so much evidence. And I think it's still debated, but there would be a model that would explain that. But again, it's a structure model, right? I'm sure there's people who know more than me here in the audience.
Yeah, I was just thinking that this puff up planet is not inflated. They're just cooling slower.
No, we know, no, because we see this in old systems as well, and there's no strong age correlation. You would see, if this was the case, you would see a strong age correlation. And there's enough information about young planets, old planets, and so on that it doesn't seem to correlate with age, and therefore is more structural, let's say, more than evolutionary process. Yeah.
And then if I may, another short question.
Sure.
So why don't you look in the UV range for biosignatures?
Well, yeah, I mean, oxygen, ozone, yes.
There is no.
Yeah, because there's UV is not, there are no facilities these days. So HST is the last UV telescope. We'll see if anything. HWO, by the way, will be also a UV telescope. So HWO will use UV to characterize. And you have, of course, very strong features from ozone, right?
Yeah.
Very obviously. So this will be used there as well. So it's not that is ignored, is that today, with the facilities we have, we don't have any capability to use the UV to find these biosignatures. But as I say, HWO will use UV as well. There has I mean, the shortest wavelengths have a lot more diagnostic power, let's say. But many of these stars don't emit a lot of UV light, and therefore, when you use indirect methods, it's not very good because you don't have root statistics. If you go to direct imaging, like HWO, then you're better off because the star doesn't do much there, and therefore the planet can be actually a higher contrast. So yeah, there will be UV. And people use UV as well to monitor evaporation processes as well. So you can go to Lyman alpha, you can go to some features also from atmospheric lines, and then you can understand how atmospheres are evaporated off of a planet. Yeah.
Good. Thanks.
Yeah.
With that, please introduce yourself, say your names, so that we.
Just visiting you today.
Yeah, good to see you.
So yeah, Ignasi, one of the results you said is gonna be very good is the estimates of the age going down to 10% error. So what are the limitations right now to get, and what is the kind of contribution that the providing these going down in its estimates? That's one question. Then the other question is, life or Darwin has been always a big issue for ESA because ESA didn't like to put money on formation flying. So has ESA changed their mind on that, or is it still the same problem?
Good question. Let me go for the first one. Age, right? Age is a hard parameter to determine in general. And actually, there's a strong correlation with the precision of the age determination with the age itself. So one can get pretty good ages for young objects because they're part of clusters, moving groups, or maybe young stellar streams. And then we have very good constraints. But when you go into the main sequence, or especially for, let's say, later type stars, late case M's, it's a gamble, actually, because there's no way to get this measurement. The technique that people use sometimes is gyrochronology. So measuring the spin rate of a star and calibrate that and get an age, but it's extremely imprecise, and there's many ways to get this wrong, let's say. Now, asteroseismology, the technique, there's more experts than myself here in the audience, but it's about measuring frequencies, and therefore you have a good understanding of the stellar interior, and that stellar interior, let's say the models will be able to reproduce those frequencies depending on some properties of the stellar interior, and therefore you can get a measurement of the internal structure, let's say how matter is distributed, and therefore from these frequency measurements is the closest asteroseismic HR diagram. Well, if you place your star there, you have a measurement of the age as well with high precision, up to 10%. And this works well also in the main sequence without any problems, which means that it expands the parameter space dramatically. Now, ESA and formation flying. You know, Proba 3 was launched not so long ago. That's going to be a test of formation flying, an artificial eclipse of the sun. There's no official statement. So whether ESA likes or doesn't like a lifelike mission. There was, this ESA town hall meetings that Carol Mandel has every once in a while. There was one, I think, this week or last week. And there was a specific question about this theme, not about the life mission or about the Darwin type concept. And the answer was not, let's say, not conclusive. So I think there's going to be, if life happens, there's going to be a technology development program from ESA to try to improve on detectors and on formation flying and on nulling techniques. In parallel, there's already developments led by Sascha Quantz at ETH Zurich, that they also already have a test bed. And I think there's progress enough to grant a technology development plan within ESA. But ICE can think, okay, my theme in Voyage 2050 was temperate exoplanets. There's HWO out there in the landscape, so let's buy in HWO. So let's provide an instrument for HWO, and so we can cross this item off of Voyage 2050.
I guess it's the long story of Darwin. Darwin was so high always.
I'm usually an optimistic person, and on this one, I'm sort of in between, not sure what to think. Yeah, it's also a very expensive mission, right? Talking about 4 2-meter telescopes plus a beam combiner. So if you go to the telescope market, a space telescope of 2 meters in diameter is not a cheap one. You multiply this by 4, and then you get the beam combiner. It's a big check that you have to write. We'll see.
You have to not mention breakthrough starship.
Okay.
Is it still going on, or is it a crazy idea?
I think it's there, because Yuri Milner put this $100 million into breakthrough initiatives. So they have this breakthrough listen, I think they call it, a number of other initiatives. Breakthrough Starship, I haven't been hearing much about it in the last 5 years. So by the way, for those who don't know, this is about flying, say, nano probes of the size of a cell phone, accelerate them with a super powerful laser from the surface of the Earth, and then accelerate them to about 20% of the speed of light, point towards Proxima Centauri, and then take data as you fly by at 20% of the speed of light, by the way. Your pictures will be a bit blurry, but anyway. I think it's science fiction. That's my take, although who knows. But the one clear thing is that $100 million is peanuts compared to the cost of this. So they should be at least 10 or 20 Yuri Milners putting money for this to happen. And I don't see Elon Musk prefers Mars, for example. So that's where he plans to go himself. I guess that's where his money will go.
Yeah, okay.
There's a soon question. Isabel?
Yeah. Hello, Ignasi. This is Isabel. So, can you hear me?
Yes, well, loud and clear. Go ahead.
Okay. So first of all, thank you very much for your talk. I'm not an expert in that field, and I find it impressive and beautiful. And so thanks so much. And my question is it's obviously going to reflect my ignorance on the field, but I'd like to know, nowadays that we are planning wonderful new instruments for the future in every wavelength, how do you see the contribution of the radio frequency in this field, and specifically the contribution of the square kilometer array for the future of this field?
Yeah, thanks, Isabella, for the question. There's also a large discovery space to be happening, and you see, here in this particular slide, it's true I have LOFAR and GMRT, but there could be also SKA in the future. There's a whole field development here that I didn't address, and there's also big here at the IAA. That's the so-called star-planet interactions. So there's a lot of research being carried out on how planets interact with their stars, whether this is observable, whether they have some kind of connections there. And for sure, SKA will have a lot to say there, because the capabilities of detecting those interactions will increase dramatically. So of course, there's a lot of potential discovery space and potential programs there to be done by SKA. And radio is also becoming big in exoplanet research. And I'm sure there's going to be more, polarimetry. There's lots of things that one can do with radio, particularly on this interactions part. And of course, and let me speculate here as well, there's also a whole area of research that's called technosignatures, right? So trying to look for not biosignatures, but signature of life, but signatures of technology. And SKA should be able to detect our own planet, so the emissions, our leakage radiation from our Earth, out to about 100 parsecs. So who knows if this would be a way to go out there. So I'm sure there's going to be this activity there as well. Anyway, that's a bit more speculative there. But in the pure science part, I see a lot of potential mostly in the star-planet interactions, and maybe more. There's more expert than myself on the radio searches. Yeah.
Okay, thank you very much. I'm sorry I couldn't be there. I could have liked to.
No problem, Isabel. Yeah.
Okay.
Nice hearing you.
Bye.
Rafa, another question, and then Carlos.
I have one. I would like to know if you have the one about the aspects of modeling. It's not a beginning which give you directly the mass of the
Sure.
difference. And when you apply this technique, the sun, you don't find the G mode.
Yeah.
So the G mode are essential to this strategy. So what to do when PLATO was detecting and the oscillation
Yeah.
in the G region.
Yeah. I think, of course, you know much better than myself here, but
Can you repeat?
yeah. So Rafa was saying that, of course, mass is not a direct observable of astroseismology, and then even in the sun, there's problems, and you need to detect the G modes to actually get a good constraint on the mass. And we don't see G modes in general in other stars, right? And the thing is that here, of course, we also have, it's not only astroseismology, but we have also spectroscopy, and we have the Gaia distances. And with everything, so with spectroscopy, you get log G determinations, temperatures. With distances, you also have constraints there. So this 3% on the mass, 5% on the radius is by using the whole collection of data, the one we'll have. And also we have metallicity, which is also an important parameter. So by collecting all this data and not relying uniquely on the determination of G modes, one can get a full constraint, as far as I understand, on the stellar properties. So that's the goal, let's say, not astroseismology only, but a collection of different measurements. Yeah.
Ignasi, thank you very much for a beautiful,
Thank you.
comprehensive, and enjoyable talk. It's one of the best talks I've listened to in the last few years.
Thank you.
Mostly for alignment as myself in the field. I was wondering how tough the fight against seeing or jittering when from space your search will be, thinking on how difficult for us is to find signals of a few parts in 10,000.
Yeah.
You are per million.
Yeah.
So can you comment on that? What are the techniques you are needing for using beasts like ELT or something?
Yeah, let's say atmospheric seeing is not so much of a concern usually, because we need telescopes more like light buckets than anything else, and we usually have long integration times, and a lot of this averages out, let's say, and there's techniques not to rely, not to be affected so much by, let's say, seeing variability. Now, what is a problem in many of these is telluric contamination from water vapor and from oxygen and ozone and everything. So one needs to correct out that telluric contamination, which can be variable over time as well. And that is one of the limitations, for example, when we go into the far red or near infrared, and there we're also developing a lot of techniques there. And of course, when you go to space, there's all sorts of other let's say, instrumental effects as well, because of the temperature variation and so on. But many of these instruments, James Webb or Ariel, are already designed to be self-correctable in a way. So that the instrument, or also even PLATO, that the instrument effects will be monitored, and we'll have the ability to correct for them. So I'd say that from the atmosphere and instrument point of view, we are on the right track. And to me, and not only to me, in general in the community, the big challenge is the astrophysics, astrophysical variability. because the star, I mean, I didn't explain this in detail, but you can get a picture of this. You have a star and you have a transiting planet. Depending on whether a star is spotted and where those spots are and how those spots vary over time, you'll have also variations in the depth of the transit, which you don't see because these spots are not occulted by the planet. So these unocculted star spots have signatures, which again, they're also chromatic. So they change as a function of wavelength because the contrast between the spot and the photosphere is also variable with wavelength. And therefore, that's the main challenge. There's this intrinsic stellar variability, granulation, for example, supergranulation, evershed flows, all these things that you guys study in the sun. Now we see that we need to understand them on stars because they are the limiting factor, actually. And that's why a lot of these precise radial velocity instruments are building and implementing solar telescopes because we don't know the sun well enough at this level of precision, let's say, and with this way of observing, then we need to understand the sun first and then try to understand the stars. So there's a lot of solar astronomers going into this kind of business because we just don't know how these motions on the atmosphere of our own sun affect our ability to find those tiny signals. We're talking about 10 centimeters per second variability and convective motions on the sun. And you can tell me that we're talking about hundreds of meters per second, at least sometimes kilometers per second. So which fortunately average out over the surface, but you still have residuals of order of tens of meters per second. And that's the big problem, more than instrument or atmosphere. I mean, atmosphere from the Earth. Yeah. Thank you.
Have one more from the chat, Jose Jairo Diaz, about the Proxima Centauri system. There are any evidence of the existence of Proxima C?
Yeah, Proxima C was announced a few years after Proxima B, and this is a long period planet. I don't remember the period or the characteristics. I don't think there's anything new besides what was published in the paper. To me, it's a bit, I mean, it's a candidate. It's not a firm discovery. And I guess when there's more and more measurements accumulated with ESPRESSO, which has a shorter, let's say, so far it's been acquiring data on a shorter period, this will be addressed, I would think. So to me, right now is a candidate. It's not a firm detection, but it may end up being the case. I mean, being a firm detection. And to me, the main, let's say, the main addition there will be ESPRESSO data.
Okay, any other questions? One final one, I guess.
You said that the M stars have more planets than other stars. Yes. And is there a theory that backs that up?
That's a good question. What I said, actually, and maybe let me say this with the right words. With our detection capabilities, we find more planets around M dwarfs than we have around sun-like stars. But we see a lot deeper in M dwarfs in terms of masses as well than we see in sun-like stars. However, of course, Kepler also can find small planets, and statistics show that when someone corrects for the biases, there are some more planets around M dwarfs than there are around, probably pretty much like twice or three times more. However, we're talking about different orbital period intervals. So within, let's say, 100-day orbital period, the structure of the system around M dwarf is very different than the structure of the system around a G dwarf, because 100 days is really close to a G dwarf and it's really far to an M dwarf. So the numbers now are favorable to M dwarfs, but I wouldn't say that M dwarfs have more planets in general, let's say, although this was probably in one of my slides, than G dwarfs. And yes, it's in agreement with what model predictions, and I really like planet synthesis models, but I think they are tuned to explain what we see, let's say. And I'm sure they can turn a few knobs and then produce more or less planets than where you want them to be, let's say. And not to discredit any of this work, which is fantastic. But I think saying that models predict that, okay, but I think you can make them predict more or less depending on what the input parameters that you use.
Okay. Well, let's thank Ignasi again.
It was my pleasure. Thank you so much. Mm.